Thanks everyone for your patience, and thanks for joining us in this rather special IDYST seminar, which is also a joint effort with CLIMACT, so the Center for Climate Impact and Action, CLIMACT for short. So this seminar today is seminar number 2 of a series of geoscience-focused CLIMACT seminars. And the idea originally came up when several of us based at UNIL and EPFL were talking about how it would be great to bring attention to the role of solid earth geosciences and geoscientists in the energy transition, which is not necessarily front of mind when we talk about climate action and climate mitigation. We have 2 presentations on geothermal innovation for advancing geothermal energy in our region. That includes Lausanne and Geneva. And our first speaker today is Dr. Chadia Volery, who is here with us in person at UNIL. Chadia and I actually first met during a meeting between GEOOL, where she works, and several members of ISTE. And we found natural synergies through our interest in brittle deformation in the Earth's crust and better understanding how those control the architecture of the subsurface and research on that topic to help advance geothermal energy here in Switzerland. And yeah, we've been in touch ever since in that meeting. So Chadia first studied at the University of Geneva and received her PhD there in 2010, I believe. Correct. After that, she joined Shell in The Hague, Netherlands. And then from 2018 to 2023, she lived in Oman to join the Petroleum Development Oman. So she has more than a decade of experience in the petroleum sector, which is actually quite interesting because she brings with her a wealth of expertise on not just the geoscientific or the technical challenges in developing resources in the subsurface, but also the economic implications and working in multidisciplinary teams. So this is expertise that I think will be really interesting for Switzerland and Lausanne in particular. Chadia will talk a bit more during her presentation about her work with GEOOL in developing geothermal energy in Lausanne. She'll present for about 20 minutes, and then we'll have 10 minutes for questions before we transition to our online speaker, which is Dr. Michel Meyer. And just very quickly, which I forgot at the beginning, because this is a CLIMACT seminar as well as an ISTE and IDYST seminar, we do have a rather broad audience today, as CLIMACT has quite a wide reach between UNIL and EPFL from different disciplines. So yeah, just thank you to all of us who are joining in person and online. And I will give the microphone now to Chadia. Thanks, Chadia.
Thank you, Anindita. Good afternoon. Is that fine? You can hear me? Thank you for the invitation. Very happy to be here to share words about geothermal energy and the effort of Lausanne to the energy transition. We'll discuss a few topics. First, we'll present what is GEOL. Most of you don't know probably. Lausanne and its plan for climate. What is the geothermal energy? Where to find naturally circulating hot water? You will see why we have to discuss these things. Then we'll go more into the geology world of geothermal energy, discussing seismic data and natural faults. And finally, what are coming to us, to you, in the next few years about geothermal exploration and development in Lausanne. GEOL is a company which was created and shared by Service Industriel de Lausanne by 50% with the collaboration of Romande Energie and ISTE. So the goal of this company, which is mainly public money, is to share investment, share knowledge, and also share risk. Because what we're doing here, geothermal prospection, exploration, before being able to develop and produce a clean energy, we have to prove that it's working fine. So there's a big risk. And this is why these three public companies have come together to share investment and risk. What you see in this slide, these two areas, is where GEOOL and the Service Industriel de Lausanne have asked and been granted by the Canton de Vaud of area where we can do geothermal prospection. Before going to the geology, I'm a geologist, so I will go more easily into this world. I would like to take a bit of time to discuss the plan for climate. What Lausanne, which is a very engaged city, is trying and doing to preserve the planet and reduce the CO2 emissions. Lausanne has a plan for climate. Hopefully, most of you know. So there are some projections, some objectives that the city would like to reach at the horizon 2050. Something which we all know, but people, more and more people, the city is growing. The projection says that in 2050, we should be 28, let's say 25 to 30% more people in Lausanne. But that comes with the wish of Switzerland, but also the canton to reduce the CO2 emission. So the objective of the city in 2050, today we are about direct emission of CO2 by Lausanne city is 300,000 tons of CO2. The objective in 2050 is 20,000. Okay, it's a wish, but it's something that set the goal. And to reach that, there are many things we can do. One is efficiency. You see that in this number. We can a bit forget the number, but the goal is to reduce the need in heat, especially we're discussing here heat, by building more efficient buildings, isolation, renovation, so to reduce what we need. But also we are a growing population to do this energy transition, letting behind us oil and gas, petroleum product to go toward renewable. And there's something we can really do to reduce CO2 emission is to change the heating system of the people and of the city. We said today that 60% of the CO2 emission in Lausanne city, direct emission, is linked to heating, home heating, and hot water. This is what is producing most of the CO2 today. So if we change the heating system, meaning we let behind us mazout, oil, gas, all these CO2 emission product, and go towards something more renewable, we can reduce the CO2 emission. So that's where we want to build a large, expand the district heating system. If we have this network of district heating, we can put the source of heat that we want in this system and bring the heat to the buildings of the city. Then you can remove the oil and gas fuel you have in each home in Lausanne. This is the plan of Lausanne today, 2022. This is what exists now to heat the people via the district heating. We want to increase that 2030, 2050 by reaching more and more people in the city. It's not only Lausanne. It's important to say that that's also an effort that is shared by different agglomeration areas like EQCAD, that's the name of the district heating, EQ or CAD-West, or EPFL and UNIL, you also have district heating, or CRICAD. So it's really the way to decarbonizing the city is to provide the buildings with district heating. But now, how do you feed this district heating? You can go with oil, but that's, you don't reduce your CO2 emission. What we will try to do, and it's more than trying, it's objective, is to replace, you see here, projection, you see the year? Yes. Today, we hear most of the heat we are providing to the people in Lausanne come from the waste incineration. So that's, I don't know if you want to call it renewable, but it's a use of something that is lost. So it's a good effort from the city. But the rest, you see, almost 50%, you have here the number of what is used today for the district heating in 2023. Almost 40% is gas still. This is CO2 emissions. So we want to replace, and we're starting now, 24, you see, 2050, 2024, 2050, 26, up to 2050 here, replace slowly in the energy mix, petroleum product by renewable. So you have the biogas, wood, heat pumps, and hydrothermal. Hydrothermal is the geothermal energy we'll discuss today. Geothermal energy. You probably heard a lot about geothermal energy. There are different types. The well-known is the shallow one, which is used to heat individual house. This is what you can find in this drawing here. So it's a geothermal probe you put in the ground, 50, 100, 150 meter depth, and you just use the heat, exchange the heat to use it for your house. What we propose to do in GEOOL and with the Service Industriel de Lausanne is to go much deeper. We'll remove that. To go much deeper, above, deeper than 1 kilometer, up to 2-3 kilometer depth, where we will directly use hot water, which is circulating in the subsurface. So that's a different system. We come from something shallow, individual, closed system, and we will go much deeper, find the natural, I will explain, natural fault and fracture at 2 to 3 kilometer depth, where the temperature is very high. Let's go back. What I wanted to say first, most of you know, but let's just discuss what is geothermal energy before how we do it. It's something which is always available below our feet. It's the heat from the earth. When you go deep in the earth, you gain, in a geothermal, normal geothermal gradient, you gain 3 degrees per 100 meter or 30 degrees per kilometer. You just have to drill, to dig, and every kilometer you gain 30 degrees. So this heat, it's natural, it's renewable, it's local, it's everywhere below our feet, always available. It's independent of winter or summer. It's always at the same temperature, and it's absolutely no CO2 emission. Once you have built the system, it's no CO2 emission. Something we want to say in GEOOL and in Lausanne is about the naturally circulating hot water. We're going to prospect, to explore, and find natural fault and fracture. I will explain what is that. It means that we're not going to frack the rock. You maybe heard about some fracking or some seismic risk in Basel, in Saint-Gall, or even Lausanne recently. There are different types of deep geothermal energy. There is the hydrothermal, what we are doing, and the petrothermal. The petrothermal, you create the permeability. So you go and you inject a lot of fluid under pressure, and you create some fracture in the subsurface. What we do here is very natural. We just go and explore for what is existing. So we have to find a way to see below our feet where are the fault and fractures, the natural one. So where to find them? If we think what we have behind our feet, 98% of the time, it's just building rocks. You have seen in our cities, molas, limestone, they used to build a cathedral or any buildings you can imagine. So the rock is tight. So there is no, and most of the time, there is no circulation of hot water. You can imagine if you go just in front of the lake, or front of Lausanne, Le Grammont, les Préalpes or the Alps, you go hiking, you have a very nice cliff of limestone. This is just tight rock. You can build a washroom or a kitchen table. So there is also this mental picture sometimes that the fluids, it can be oil, gas, or water, is in underground lake. That's also exception. in the big reservoir of petroleum history, oil, gas, or we can discuss water, the fluid is in the tiny pores of the rock, like a sponge. You can imagine a sponge or tuff. In Switzerland, you all know we don't have a very negligible oil and gas reservoir. We have no history of petroleum industry because most of the rocks are tight. So what we are looking is where the rock is broken, naturally broken. That's what we call natural fault. Switzerland, here, this is a tectonic map, so geological tectonic map of Switzerland, where you see the different, what we call structural tectonic unit. This, you recognize maybe in yellow, is what we call the plateau Suisse, or bassin molassique. It's this flat part in Switzerland. Here, you have the Alps, the Prealps and the Alps, and extern, you have the Jura. So that's what is given to us. That's the cards, the play. And now we have to find the natural fault and fracture. And you see in this big map, there are some we very well know that it's called Aubonne-Pontarlier, for example, or La Sarraz, and they cut into the Jura mountains. Here you see the two areas of research that we have in Lausanne. The two areas of research are here, and what you see in black, this line, are the historical petroleum seismic line. This is where there was some data acquisition to have an idea of what is below our feet. So that's seismic data. So you can see that there were a lot of effort in the past to find oil and gas with not much success, with some exception. But you see also that where we have the area of interest, the two area of research, there's very little data because the city was here, so you don't go and do analysis as easily as you want. There are also some deep wells. It's good to know they are from the 70, 80 that go to 2-3 kilometer depth. You see here the depth, but they're also outside the area of interest. So the first step we had to do is to find data, to acquire data to get an image of the subsurface below our feet. This is where seismic campaigns are so important. That's the indirect way and one of the best way to, let's say, illuminate the subsurface, the geology below our feet. So what we do, and you probably already know that because in 2023, we have done a seismic campaign. We call it 2D, meaning that some seismo trucks, these trucks, they travel along a road, along a profile, and they create and provoke seismic acoustic waves. They propagate into the subsurface, and when they reach a geological layer, which has physical property different than what is below, they will reflect. So behind the truck, we put geophone. And in this geophone, we listen to the signal, to the waves. It's just like that, to the wave coming back. And the time is what we record and the amplitude. And from that, we can create, like an echography you have in a medical ward, you can create a picture of the subsurface. Here, it's an example of a picture we acquired in 2023. What we see in this one is the molasse. In this area, plateau Suisse, bassin molassique, we have up to 1 kilometer, 2 kilometers of molasse. So this is sandstone, shale. And then you go into limestone, mainly rocks. And this limestone you see here with some color, we call reflector, the line we can continue. And you will observe at some location, they are interrupted. This is a fault. And it's a natural fault because this fault has developed linked to the orogeny of the Alps. Because Africa has collided with Europe, you start to deform the rocks and you break them. And this is where sits the geothermal potential, the hydrothermal potential of Lausanne subsurface. Other example, very continuous reflector, tight rock, no water circulation, but here, this is the area of interest for us. And last one, just to show you this, for example, comes from southwest here and goes to the northeast, it goes for 10 kilometers like that. So you really have a profile of information of the subsurface. So GEOOL would like, and with the support of the Swiss Confederation, has identified a few locations with geothermal potential. So we have a portfolio of structures, I mean geological structures with hydrothermal interest. And the most promising today, it means that the one we have the highest confidence that they exist, because it's all information which are scarce or indirect, we will place a well. So we have a few structures here in the southwest. We have some, we call it positive structural flower. We also have negative. And we have also the front of the halp, the truss there. Sorry. So this is the project we have. Soon is to bring a well, a deep well, and to drill to almost, I have to move these things, 3 kilometer depth. On the left, you have what data we have. So this is reflectors. It's not a picture, it's just time. The Z scale is time. How much time needs a seismic or acoustic wave to travel in the subsurface? From that, we create a geological model. So this is a summary, a diagram of how we see the subsurface in Lausanne. So the reference site is EPFL, or I should say UNIL. We will cross 800 meters of morass up to 1 kilometer. This is not interesting in terms of geothermal, deep geothermal project that we want to do with GEOOL. And we will go into the interval of interest. The main one is what we call the Malm. So it's the Upper Jurassic. That's the age that goes around 150 million years. And at this depth, we start to have temperature, which is very interesting to use and to provide the city with heat. So we'll go first with a vertical well up to 2.5 kilometers, identify the rocks and the depth. It means calibrate the underground, the understanding with indirect data, know exactly which rock we cross, which is the depth. And then we'll go with a deviated sidetrack, deviated arm into the fault and the fractured zone. And here we have the objective to find naturally circulating water. It means that we'll just use what is there, and it should be around, we have different models, 40, 50, 70 degrees. So what is next now in the calendar of GEOOL? Two things we are doing in parallel. One is to come with the first well. It takes a lot of time. You have to ask authorization to the canton. But we have identified the subsurface targets. And one of the main challenges now, and which is absolutely normal, is to find the land plot. Because you need to bring a big platform, big rig. And this is really not the easiest things to do this day, is to find the surface location where it's empty enough, then we can put our rig and drill to the subsurface target. So if anybody of you has a land a bit west of here, please, you contact us. We'll be happy to discuss. And the second thing we will do, and this is already planned and authorized by the canton with a few exceptions, we have done a public inquiry. We'll do a 3D seismic campaign. It means that before you have seen that we had 2D seismic line. It means it was very scarce information along a few lines. Now we would like to do it everywhere. It's not everywhere, but every the distance is very small, to have a very dense network of line where we have seismic data. So this is what is it's cooking now. It will be for March, if everything goes well, for March 25. We'll go through the city with 3 groups of 2 seismotrucks and do what you have seen before, just vibrate and record with geophone the signal of traveling seismic waves.
Okay, I can see that Michel has been online for quite some time now. Hello, Michel.
Hello, everyone.
Okay, and everyone can hear Michel quite well in this room. So thank you for joining us. Dr. Michel Meyer is our next speaker, and he's joining us online, I believe, from Geneva. Yeah, thank you and welcome. Michel also received his PhD from the University of Geneva, like Chadia. He started out as a geologist at the Service cantonal de géologie in Geneva, and then became directeur du service de géologie sols et déchets. From 2011, he has been at the Service industriels de Genève, where he was head of the geothermal energy for 13 years. And more recently, this year, he took up a role as head of thermal and solar energy in the same organization. So Michel and I never met personally, but there's a really nice little outreach video by Michel, which was produced by Science Escape. And here he compares the development of geothermal, of the geothermal sector in Switzerland and France. So it's a nice little video and it's a testament to Michel's excellent communication skills. So today, Michel will talk about what's happening in the geothermal world just down the lake in Geneva. And thank you for joining us. I'll hand over the microphone to you, Michel.
Thank you so much. I hope you hear me, but it seems that it's okay. Well, I'm sorry I'm not with you in Lausanne, but very happy to be online. I'll try to share my screen. So very happy to share this with you. I will talk about developing geothermal production and storage for Geneva's energy transition. And you will see it's quite close to what Chadia showed, because actually we are working on the same topics, the same targets, in the same type of structures, geological structures, but also the same type of enterprise. Well, as mentioned, I'm working for SIG. SIG is a fully public company. It's owned by the state of Geneva and Geneva municipalities. That's a utility active in many fluids, but also active in the world of thermal energy, providing some thermal solutions. And well, actually, that's exactly the same issue that Chadia showed. We are mainly covered by oil and gas today for heating purpose. This heating purpose represents approximately 50% of the energy consumption in Geneva. And as you see on the map on the right-hand side, all these blue dots represents the gas boiler, and the red dots are the fuel oil boilers. There are some small green dots appearing in the system, but it's not going very fast. And that's part of the discussion. And as in Lausanne, we decided to try to develop our district heating networks in order to phase out from gas, to decarbonize our energy systems. So we already have a district heating system in Geneva, existing one, but not so big. What you see in red there, that's a district heating. What you see in blue, that's a district cooling. 2 different district cooling, one's fed by water from an aquifer, and the other one fed by water from the lake. But actually, if you focus on the district heating, the red one, today it's representing, or it's covering less than 10% of the heat demand of the Geneva canton. And actually, we would like to increase the amount of energy delivered by this type of infrastructures. Today, this infrastructure is covered by a waste incinerator, recovery of heat from a waste incinerator, and the rest is covered by gas. And well, in order to increase this amount, we had a votation in Geneva 2-3 years ago, and the population of Geneva gave a monopoly to SIG in order to develop these district heating networks. And actually, we are going quite fast now in order to develop this district heating. You see in orange the branch that will develop as a district heating. In light blue, you have the district cooling system that will be developed as well. And that's huge investment that will be done during the next 20, 30 years. Today, this year, it was more than 100 million Swiss francs invested in order to increase this district heating network, but also to provide some renewable sources, because that's part of the discussion with the population. We obtain a monopoly, but actually we have to feed this network with at least 80% of non-fossil heat. So that's why we are working in the same time, not only in the development of the pipes, but in the development of the producers, working on sewage water sources, lake water sources, some waste wood incineration, some wood boiler, recovery from data center, and so on. And of course, in this discussion was the discussion about geothermal energy. Is geothermal energy a solution in order to feed this network? And not only this network, also for a solution outside these networks. And that's why we launched approximately 10 years ago. Yes, that was in 2014. We launched the Geothermal program. This program is piloted by the canton of Geneva and implemented by SIJ. And we are working together for more than 10 years in order to explore the underground, to better understand the Geneva underground, but also to work in an holistic way on several different axes, like the legal framework, the regional coordination, the data management, environment and sustainability issues. So we were trying to not only to better understand the underground, but also to develop a framework, an institutional framework favorable for the development of geothermal energy. And actually, we are working on all types of geothermal energy. What you see there, the number 1, number 2 is already very common on the market. That's heat probes, heat probe fields, already well developed. But we worked a lot on the number 3 and number 4. We worked a lot on the characterization on the quaternary aquifer, shallow cold aquifers, the number 3, but also exactly the same target as Chadia showed before, the number 4, Mesozoic fracture and karstified limestones that are existing also under our feet. Another axe was to work on the prioritization of heat and cooling sources. It means that we would like to provide as much heating as possible with heat sources hot enough without heat pump. And the same for the cooling. We would like to provide cooling solution cold enough without cooling machine. And it means that's why also we prefer the network solution if such a source exists but isn't directly accessible. And that's why we have this huge development of networks. And we presume that this network will cover in 2050 more than 50% of the heat demand. It's less than 10% today, and it will be more than 50% in 30 years from now. So we also have to find the resources in order to feed these networks. And of course, we work on a territorial energy strategy, what we call the merit order of energy. We would like to use first the waste heat from the incineration, heat from the incineration, for instance. And then, as mentioned before, we'd like to valorize the deep and medium depth geothermal energy, which is hot enough in order to supply heat without heat pump, or not only with heat pump. And then we go to the world of the heat pumps. We would like to valorize the shallow geothermal heat pumps and hydrothermal heat pumps, hydrothermal in terms of water from the lake, and then only the air source heat pump. And finally, you see that the biomass, the wood, and the renewable gas is very low in our merit order because we prefer to use this type of resource for very specific uses. If you need high temperature, for instance, in the industry, we will dedicate this type of resource for these very specific uses. because we think that for heating, we can make it with the other resources. And we were quite active during the last 5-6 years in the world of thermal storage issues and opportunities. Geothermal storage, I mean, because there are some issues, there are some thermal issues. We would like to have a better valorization of our industrial waste heat during summertime. For instance, today, the waste incineration that we have covers more than the need that we have on the existing network. So it means that we have an excess of production today of waste heat. And in the future, we presume that we will have some excess of production of renewable during summertime. For instance, if you can have some doublet geothermal, deep geothermal doublet, it will not be used in total during summertime, and it could be very interesting to try to recover this heat and to store it in the underground and to reuse it during the following winter in order to improve the efficiency. And if we are working in these issues of merit order of energy, is also for electric issues, because we would like to limit the peak demand of electricity during some winter time. There are some risk of shortage. We have today a limited quantity of renewable electricity produced. We would like to limit the carbon intensive electricity consumption as well. And this high CO2 emission electricity is mainly used during winter time. We would like to make the most of excess of renewable, and I mean of excess of electricity, renewable electricity during summertime, because it's also low CO2 production. And for instance, we launched a project of power to heat. Would like to make the heat pump work during summertime with excess of production of solar PV in order to produce heat that will be stored in the underground and reused during the following winter. And we are also very engaged in this topic because we are a GRD, we are a grid operator. And we know that if we only use or develop the less efficient renewable thermal solution, we will have a great need in grid reinforcement, and it's also a lot of costs. It's not only the production of electricity that is a problem, but it's also the reinforcement of the grid, the distribution of electricity. So if I see what we did in the field of shallow aquifer, less than 100 meters of depth, that's quaternary aquifer. We drilled more than 150 wells during the last 10 years. A lot of pumping tests, analysis of the quality of the water, just to see how the water flows, what is the slope of this aquifer, and so on. And today we launched the first exploitation of this type of aquifer, providing cold water, because this water is 12-30 degrees when it's at natural temperature, and we can use it as free cooling solution. We can also use it as a heating solution with the help of heat pump, but we are also using this type of aquifer as buffer in order to store excess of hot water or cold water, so as a storage solution. And an example is that just to show you what we did in the vicinity of our major district cooling network, what we call GENILAC. GENILAC is a huge network fed by water from the lake. This network is under development with a lot of investment done, and it's providing cold water to the center of the city, to the zone of the airport of Geneva. So it's offering some free cooling solutions, but also heating solution with the help of heat pumps. And for instance, on the orange zone, the sector of the airport, it's working like what we call an energy loop. It means that in this zone, the consumer are exchanging their calories. The one that are producing hot water when they are cooling the building, this hot water is reused by the others who need hot water in the same times. So there are some exchange of calories in this network. But as you see on the right-hand side, the curve that you have, the blue curves represent the coal demand all year long, and the red curve represent the heat demand. And you see that you have an excess of demand of heat during winter time, of course, and an excess of cold demand during the summertime. And so it means that we have to balance the differences of temperature in this network all years long in order to offer the quality of resources the consumer needs. And what we see on the left-hand side on the map, you have a red dot. And this red dot, on this red dot, we drill several large wells in a shallow aquifer. And we are managing we are regulating the temperature of the network with the help of this aquifer. And this aquifer is working as a buffer as well. It means that it's a low temperature seasonal heat storage solution as well. So many things done at shallow depths, but we also worked a lot, and most of the investment were done on this topic, the medium depth geothermal energy, because when we launched the program 10 years ago, we already knew that there were some promising aquifers, or we thought that there were some promising aquifer between 500 and 2.5 kilometers in calcifies and natural fracture limestones. We expected temperatures of 30 to 90 degrees, but actually, as you know, as we don't have any oil and gas tradition in Switzerland, there was a huge gap in subsurface knowledge. So that's why we launched an important exploration program with the help of the Federal Office of Energy, but also with the help of University of Geneva, for instance, that helped us a lot in this topic. And between 2014 and 2018, we launched a lot of 2D lines, 200 kilometers of 2D lines. We also reused and valorized the existing data. And on this basis, we were able to drill the first two wells, the GEO1 well, 750 meter deep, and the GEO2 wells, that was 1.4 kilometer deep. That was exploration well that was not done in order to produce. But actually, the first well was very, very productive. We got 50 to 70 liters per second with a temperature, an average temperature of 34 degrees. And well, that was great. That was a great news for us. That was the confirmation of this type of geothermal energy will be available in our system. And we produced this well for months, and we learned a lot from this well, following in the meantime a lot of water springs at the foot of the Jura Mountains and so on. So we have a better understanding on how it flows. The second well was done in a completely different geological context. We chose this geological context because it was different, but there, unfortunately, the flow rate was really low, less than 1 liter per second. But actually, we learned a lot from this well as well. There were a lot of geological surprise in this well, and it gave us the last reason in order to launch a 3D campaign. So that's what we did at the end of 2021, a very large 3D campaign covering nearly the whole territory of the canton of Geneva, all the very dense urban zones. So that was a great project, very difficult to organize, but we managed it, and we got a lot of very important results. One of these results is that our structural network, the orientation of the faults, the presumed faults, was completely different to what we saw 10 years ago. We already knew that from the 2D lines, but the 3D gave us a very good view of what is the actual fault orientation in the canton of Geneva. Instead of northwest high-slip fault, we are very developed east-west structures. And we better understand why our GEO1 well was very productive. It's really well situated regarding the position of these faults and these kartic features. And it was not the case for the GEO2 wells. So now we presume that we have the key in order to develop massively this medium depth geothermal energy. We are working on a very ambitious plan of development with more than 10 to 15 doublets. What you see on the left-hand side, a red circle represent the doublets that will be dedicated to this large network that I showed you at the beginning. The blue circle represents some other doublets that could be developed in order to feed some decentralized, smaller networks. And what we see, what we presume today, is at the end, we will have several doublets connected to a large interconnected network. Some of these doublets will be quite deep in the Dogger and might produce some water at 80, 90 degrees. And some others will be shallower in the upper Jurassic units and might produce water at around 50 degrees. And what we presume is that we could use these existing production and distribution infrastructures as a storage facility as well. Because as I mentioned before, during summertime, we will have an excess of production of heat from the deeper doublet that could be valorized in a shallower doublet, that could be stored in a shallower doublet in order to improve, to enhance the temperature of the shallower doublet and to have a better efficiency at the following winter time. So our next doublet will be drilled next year, 2025. That's under preparation, and it will be a 1.5 kilometer deep doublet connected to this large interconnected network. They are quite close to the end. I just want to show you that that's the situation of today in the network. What you have there, this curve represents the heat demand, the average daily power in the existing network. You see that during winter time, you have a higher demand, and during summertime, a lower demand. And you see the energy mix in this network today. 55% is waste incineration, and the rest is gas. And I will press the button, and you will see years after years what we presume in terms of development of this network and the implementation of the different producers in this network. And you will see slowly coming an orange band. This orange band might be the geothermal doublet connected to this large interconnected network. And you see this merit order of energy as well. The base load is done by the waste incineration, the wood waste incineration. And then you have this medium depth, this orange band, the medium depth geothermal energy. And then you are using the sources that requires more electricity with heat pump. And okay, what we see there in 20 years from now, we may have part of our goal done. But actually, we would like to phase out from gas. We would like to be carbon neutral at that period of time. And even if we have more than 80% of non-fossil in the system, there is still a lot of gas in the system. And one way to decrease this gas content is what we said before, to use this excess of production of heat, geothermal heat during summertime, to store it and to reuse during winter time. And another thing is what we really already do, or we're already doing, is working on the sobriety, efficiency, and building retrofitting in order to decrease the heat demand. So that's where we are today. That's my last slide. That's quite complicated. That's the Sankey diagram that represents our energy system in 2050. And actually, you have a lot of resources on the left-hand side. You have different uses on the right-hand side. And what I just wanted to show to you is that shallow geothermal energy and medium depth geothermal energy is in the system as a producer, as a resource, but is also in the system as a storage solution, could be used in order to better valorize the waste heat and to have a general efficiency better than without these storage solutions. So that's what I wanted to show to you. And of course, ready for some questions if you have some. Thank you.